So good evening. Thanks for coming. My name is Bob Lambert, and I was one of the co-founders along with Monty Robeson, who's maybe snuck away. So we've been at this for a lot of years. We built the place in the year 2000, so we're into year 19, and it's been a pretty good success. It's all done by amateurs. We raise the money ourselves, designed it, build it ourselves. Most of you have heard this speech. Anyway, so we're pretty proud of it. We do real science. Isabella, are you in here? So this is a high school senior from this high school who's doing very well as a volunteer here. It's a joy to have around, and a good worker. So tonight's talk is about what we call the NASA's Great Space Observatories. And this is an initiative that started a long time ago. So we're going to give a little background of how this started and what was the driving force to do something as outrageous as what this was when it was first conceived. So this is telescopes teaming up for great space discoveries in multiple wavelengths. Turns out if you're going to do great discoveries in space, you're probably going to do multiple wavelengths to really figure out the science. So you need a lot of instruments. So the build-up in reality is this amazing, ongoing, and successful journey. And so it's a thank you to the guy who dreamed it up, a guy named Lyman Spitzer. We'll talk a little about him. So this has mostly happened in my lifetime, and I was, for the most part, oblivious to how this was rolling out. You know, we didn't have instant information like we do now. So I learned a lot in studying for this talk. So in the beginning, which is the beginning of the 20th century, in the early part of the 20th century, there was one modern reflecting telescope, meaning telescopes that use mirrors that have big mounts. And that was installed, a 60-inch instrument. That was a breakthrough in mounts and mirrors. It was on Mount Wilson, north of Pasadena. In fact, it's still there, and it still works. So it was a pathfinder, and intended to be a pathfinder for a great 100-inch breakthrough instrument to come. And that was being designed, so they were testing how to do this and made a very viable telescope in the process. It's a wonderful, highly accurate instrument. It was completed in 1908 by Observatory founder George Ellery Hale, who was a famous name in the beginnings of modern astronomy, and funding from Andrew Carnegie. So it's an awesome device. This is a 1908 image of the Great Orion Nebula, which you can look at tonight. I'm sure there's some telescope pointing at the Orion Nebula tonight. It's always a wintertime favorite for us. Then here's a 2016 image done by an amateur with the 60-inch. That is a pretty good picture of Saturn and its rings. So this is a beast, still operational. They don't use it for science. You can rent it for a night. Take 20 of your best friends, go out there and rent it. And it's not all that expensive when you have a lot of people, but it works great. So these things were, built to last. Don't know what happened there. So, soon there were two. 1918, 10 years later, the 100-inch Hooker telescope, named after an industrialist in Los Angeles, was also done by Hale. At that time, it was still widely believed that the sun was at the center of the galaxy, and our galaxy was the universe. Cosmologists believed that the galaxy was the universe then, when they turned on that telescope. My father was 2 years old, and they still thought he didn't know that that's what they thought, that the universe was our galaxy. So they came up with this thing. It was 2.77 times the light gathering power of the 60-inch. Great progress in making mammoth instruments. Game-changing instrument. This did accelerate the evolution of astronomy in unimaginable ways. It was an astounding success, and the discoveries that came out of this thing were every bit as awesome as the discoveries of people landing on the moon, and the newsworthiness of what came down from that mountain was stunning to people in the 20s and 30s. So Edwin Hubble used this telescope to establish that spiral nebulae in what we thought were in the galaxy are in fact distant galaxies outside our Milky Way, and that all but two that they studied were moving away, indicating that the universe is expanding. And the further away they were, the faster they were moving away, which was the big discovery. Over the coming years, it revealed the vastness of the universe for the first time. Our Milky Way is just one of what they call these island universes that were everywhere they looked. This, as you can imagine, this is a big deal. So the 200-inch telescope plan began because of the discoveries there. Unfortunately, they had a long wait due to a war. They got most of it built before the war, but it wasn't really assembled and get the mirror up to the top and get it all working until January 1949. So 31 years passed with the 100-inch as the premier instrument. People were agonizing over the fact that we couldn't get this next telescope, but nothing you could do. And there really wasn't a larger instrument in plan or funded at that time. They wanted to see how this thing would do before they took the next steps, because you're putting a lot of mass up there. As you can see here, this is the 200-inch Hale. This is an actual person down there. Whoops. This is not some little decal on a wall. This is a person, so the scale of it. My wife and I drove up there and get to look in the windows and see this thing, and it was a gasp kind of a thing to see. It is so monstrous.
Don't they have a seat inside of that?
Yes.
The prime focus, you can actually sit.
Yes. Well, actually, that
there.
was. We're going to get to that point, but yes. So this is the world's largest telescope for almost 50 years. So 31 years from the 100 to the 200, and almost 50 years to something more powerful. That's a lot of years of not having all the discoveries that we want to have. This thing is still in full use. It's not been retired. You can't rent this. And it's still very competitive to get time on this instrument. It is pretty spectacular. So this is certainly a tribute to the people who took the risks to make these things. So how were these two telescopes used? Back to the point about sitting in a chair. There were three ways that it was used. Eyepiece observation, three that I know of anyway. People 60 feet up above the ground on the top of this mountain with the aperture open, freezing, unbelievably cold. Even on summer nights it could get pretty cold on a mountaintop. And so that was not a really good deal. But they did it. Spectrographs, and then countless film plates, 4.5 or 4 inch by 5 inch or 5 by 7 inch film plates. Hundreds of thousands of these between these two telescopes are archived and referred to quite often in studies, because that's information that's many, many decades old, and we can compare it with today's. You can see things changing. So it's valuable information today. So it's been a great workhorse with countless discoveries, still going strong. If you get really interested in all the discoveries, there's plenty of websites that explain what they learned and how they learned it. Most of it written so mere mortals can understand it. But we have to back up 2 years, 2.5 years. 1946. This is when the visionary notions of Lyman Spitzer occurred. He was an astrophysicist, theoretical physicist, a visionary. He said, we have to put observatories in space. We can make bigger and bigger land observatories. They're not going to tell us what we want to know about what's going on out there. So we need to examine the unobservable parts of the spectrum. Remember, basically all they could do was visible light. He developed the theory and rationale. The need was strong. Of course, there was great controversy over such mundane things as feasibility, cost, value, just overall doability, but the seed was planted. This was 11 years before Sputnik, 35 years before the space shuttle, so how they'd launch it, it was, TBD. Figure that out as we go. And the only rocketry that was known, basically, we knew a lot about rocket science, but the only proof was 12,000 V2s being fired from Peenemünde into terrorizing the populace of London. And those things go very high, nor were they well guided. So here's what he said: to grasp the words of the cosmos, wonders of the cosmos, and understand its infinite variety and splendor, we must collect and analyze radiation emitted by phenomenon throughout the entire electromagnetic spectrum. Those are his words. And he got people to rally around very quickly. So the years of science using the 100-inch had unveiled the idea of a vast and unknown cosmos. So the game had fundamentally changed. He recognized that and said, well, you know, we had a lot to do. The tools were inadequate for the challenge and could not ever be made adequate in the visible wavelength part of the spectrum. You can get better and better, but still you're bound by the electromagnetic spectrum, the visible light. Roy G. Biv, right? Red, orange, yellow, green, blue, indigo, violet. A lot of you remember that. A lot of you don't want to remember it. The Mount Wilson discoveries revealed a huge problem. Tiny glimpse of spectacular universe could not be explored sufficiently. Remember, this is 46 before the 200 inch. Less than 1% of all light that comes to Earth is in the visible spectrum. There's no way around it. It's physics. It was not possible to research what the universe was made of and what was happening. So you got to do it. So the rationale for space is pretty obvious. Lots of serious limitations. So here's the long list of issues on Earth. Atmosphere being the biggest part of it. But with that came weather issues, light pollution, dust, earthquakes, fires. We've had panics on Mount Wilson over the fires in Northern California in recent years. These fires come right up the mountain, and they put a lot of people with hoses out there trying to keep the thing from burning down. It's pretty close to the fault line. So limited range of pointing from any location. If you think about it, you can look horizon to horizon from the top of a mountain, but you can't look at anything other than what's up at that night. So you can't point everywhere. Full moons, cold weather, winter snow shutdowns due to hazardous roads, huge temperature swings, nighttime only. Summer nights are pretty short. The nights you'd be comfortable up there are short nights. Huge scopes require a lot of maintenance. They have problems. Invisible light only. So now we go to space. All the sky is reachable from one instrument. You can plan observations anywhere you want. No atmosphere, no weather. And even though it's very cold, it's a steady temperature. So your optics, everything is stabilized all the time. It doesn't change. No moon or sun interference. 24/7 operation. There's no day. There's no sunlight hitting the atmosphere. So you can take very long exposures. All wavelengths accessible. But to get them all wavelengths accessible, you need 4 instruments to get the wavelengths you want. So they got to do 4. Hence, 4 space observatories were planned over the next decades. So they cover from infrared to gamma rays. Everything but radio and visible. Although the Hubble basically is a visible light instrument, but they were part of it so they could get outside the atmosphere. Great new ground telescopes for visible and radio wavelengths. So we call them observatories, not telescopes. Why observatories? Well, they do, in that system that's out there, that's one of these, they do a lot more than what the telescope, the mirror and tube and all the things do in a ground telescope. So they really were fully operational observatories. So they were the Hubble, the Chandra, the Spitzer, and the Compton. They were all, each had a team, and they started investing and started doing the science. The Hubble was launched in 1990. It was a 4-year delay because of the space shuttle disaster, because that's the launch vehicle. Then it took a little over 2 years to get the mirror properly functional. So it really started in 1993 to be late 92 to be fully functional. And they've had 5 service missions, including that first one. It's dramatically more powerful today. It's a 3rd generation Hubble that's out there today. Chandra X-ray launched 1990, the same year as Hubble. The Compton was launched the next year, 1991. It lived 9 years. Then the Spitzer, the infrared, launched in 2003. So they were all launched at pretty much the same time, similar times. The Compton lasted 9 years, so it did great work. None of them were guaranteed to last a long time. They put pretty conservative estimates of their useful life, but they far exceeded. So the Hubble, the only one that can be serviced in space. So it was operational in 93, right at the beginning of 93. The Compton lived until 2000. The other 2, Chandra+Spitzer, still operating well. These things they have gyroscope issues now and then, but they can manage them. So these are partners in exploration. The idea is that they search in their wavelengths and join together for new science when any one of them makes a discovery, or if there happens to be a sudden event that you clear the decks and point everything you can at some event and figure out what it is, and they can do that. And they have freedom from Earth night only astronomy and freedom to build next generation instruments for every wavelength. So everything that's been built has been a pathfinder for the next one. And you'll see that here. So here they are, amazing instruments. They all look different, but only 3 of them have these long tubes. The Compton has actually 4 telescopes in it. And they cover from gamma right to there, to radio. Middle of microwave to radio, they don't cover. So the Compton was named after Arthur Holly Compton, who's a Nobel laureate for gamma ray physics. It's 4 main telescopes, each one doing different wavelengths, and operational till 2000. Gamma ray and X-ray both, although it was mostly gamma ray, but they did go into X-ray. And so it was to survey natural sources of gamma rays across the universe. Little was known about gamma rays in that era, very little. And they detected more than 2,600 gamma ray bursts, so that it made astronomers realize that these bursts occur throughout the universe. So the next generations had to learn what's causing them. They could measure the burst, but they couldn't measure what was going on behind them. So since the Compton, we've had the ESA Integral spacecraft, NASA's Swift Gamma Ray Burst mission that looked at the very heavy metal gamma ray bursts, and NASA's Fermi Gamma Ray Space Telescope. All 3 are operational today. So the longevity of these things is pretty amazing. So the Spitzer is the 4th and final of NASA's great observatories. It's in solar orbit. The others are in closer orbits. And it measures heat radiation from objects in the galaxy and the whole universe. So infrared is heat. And this thing is good at infrared. So it can look through dust. It can look through gases. Dusty stellar nurseries, the centers of galaxies, newly forming planetary systems. That's the focal point of this thing. Giant molecular clouds, organic molecules that may hold the secret to life on other planets. So this thing has turned out to be pretty good at identifying organic molecules, of which there are many. So it has unveiled some of the biggest surprises in space, mostly because it can look in places that the others can't. So the Chandra is X-ray imagery throughout the universe, examining black holes, including the Milky Way supermassive black hole area, and looking and finding that every spiral galaxy that it looks at has a supermassive black hole in the middle. It can easily see that from X-ray emissions from things around the perimeter of the black holes. So studying new supernova, galaxy collisions, galactic nuclei, galaxy clusters. The Chandra's there. Much partnering with Hubble. And they even have detected X-rays from Pluto. Huh? So, Isabella, your homework assignment is to find out why there are X-rays emitted from Pluto.
Alright.
Huh?
Okay.
You'll do it. I know you will. You probably have the answer by the time we leave the room. Google it. So, that's pretty peculiar. When I read this, I was shocked. What? So we own, in this room, is the only piece of the Chandra mirror system that exists on planet Earth. And it's right behind this screen. And it's very cool. So the Chandra X-ray, the mirrors don't reflect, they deflect. And so you have 8 of these giant barrels that are very precisely curved to deflect X-ray light and reduce its energy level so it could hit a collector and be captured. So we have the only one. We're very proud of that. After this is over, I can lift it up and show it to you. The Hubble Space Observatory, a rough start, we know that. But now it's had over 25 years of what anybody would call spectacular science discovery. And great new instruments were installed on the last servicing mission, which is in 2009. So 10 years ago was its last and will never be serviced again. But it's working so good. It's way better instrument than ever before. So it works today, everything from space weather on Uranus. There was something published the other day that showed climate change on Uranus and Neptune, both, to discovering Ultima Thule. The people that sent the New Horizons out past Pluto called the Hubble people and said, you know, we got a lot of fuel left. We want it, but we can't make big changes. Find us something we can go and fly by. And the Hubble team said, okay, and they did. So that 22-mile long thing we call Ultima Thule, you've all seen that in the press, you can't miss it, was discovered by the Hubble. 22-mile long thing, over 4 billion light years out, no problem. Pretty impressive. So the test of how good it is, in the first many years, you were only allowed to get a small amount of time to do small projects. Except there are a couple exceptions to that. Now they're encouraging long-term projects. Bring us challenging projects that might be multi-year because it's working so well 10 years after its last servicing mission. That's mind-blowing. And there's also a good part of what it's doing now is pathfinder work for the James Webb Space Telescope, which is, you know, in the 20s they're going to say, you know, here's things that we're looking. So the James Webb team is working with Hubble to set up observations for the James Webb. So they're really fused at the hip. So the Hubble, widely considered, you won't get much argument on this, is the most important science instrument in history. That's quite a statement. So keep that in your mind. The Hubble is the real deal. So I'm going to show you an example of using multiple space observatories to research a galaxy. It's the Pinwheel Galaxy, very famous. It was discovered in 1781. It's 21 million light years away, so that's like a little over 8 times further away than the Andromeda Galaxy, and 170,000 light years across, which is 40 or so, 50% bigger than the Milky Way, and about 1 trillion stars, which is pretty comparable to Andromeda. It's hard to count them. They have 1,264 known star nurseries, which are these giant hydrogen clouds, a bit bigger than the Orion Nebula in the spiral arms. That's a lot of discovery. So here it is. I'll just quickly whip through. This is a famous picture taken by the Hubble of M101, the center part of the spiral arms. Here it is in infrared. So they use false color to make them uniform color. So infrared light highlights the heat emitted by dust lanes in the galaxy, which is where the stars are forming. visible light from the Hubble. Most of this comes from stars, and they trace the same spiral arm structures. This is how we know where star nurseries are, through these kind of observations. And here's Chandra X-ray images. So everything in blue here is X-ray emission. And throughout all the spiral arms, and then all these things out here are X-ray from supernova explosions of stars. So these are stellar explosions. And here you put it all together, and you've got some serious science that people, they've been studying this. They go back and image it over and over through the years and can see how it's evolving. If you look at the blue dots, you can see all of those. So this is an incredible display of the cooperation of the telescopes to do science. I'm not going to do this one, it takes too long, but there's a cool website that shows the Hubble and the Spitzer working together. It's like a 3.5-minute video. So here's the Hubble 1999 image before the wide field planetary camera 3. This is the 2, and it's kind of this blobby. There's a horse's head here, and this body kind of looks like a moose's head, I think. We spent time in Maine, so we focused on moose. So they put in a new camera, and look at that. That versus that. So here's a horse's head now, and they've taken away a lot of the gas in this thing. So infrared light cuts through the gas and dust. But this, remember, there's more, you go further into the infrared with the wide field planetary camera 3 than you did with the previous one. And then here's the Spitzer. Here's deeper infrared. Where'd the horse go? So now you're looking through, you can actually see things that are behind it. And this attribute of infrared is what makes it so valuable. They can see through gas and dust clouds that the other telescopes can't. So they can look in many places and discover more things. So they really do work together. And here's 3 are better than 1. The Chandra, the Hubble, and the Spitzer working together. And I don't even know what the object is. So what amazing progress. Really, in a blink of a cosmic eye, the space telescopes have unveiled so much and added so many new mysteries. And you kids have to understand this. The more we discover, the more mysteries we unveil for you guys to figure out. So we wanted to leave some things for you. You should be delighted that we haven't. What if we'd found it all? That would really be dull. No, we're barely started. We've barely started. So the future's spectacular. For the long run, what's been done is really just proof of concept. It's fabulous proof, but it's real science. It's not somebody conjecturing, some philosopher. It's the real deal. And that's unique in my lifetime, basically. So the James Webb is coming. We're going to put LIGO-like things out in space to get gravity waves. And there's a lot more that I don't know about. So how many space observatories are there now? 5? 7? Nobody knows, do you? None of you know. Space telescopes are everywhere today, monitoring Earth. Planet Lab has launched 300 recently, the size of a loaf of bread, used for surveillance by militaries, for astronomy. I'm not counting those. I'm only counting astronomy-related things. How many astronomers using? Let's count them. Here's the list. Hubble, I saw it, put stars next to Hubble, Chandra, and Spitzer. And you notice NASA. 2 of them are ESA only. ESA has collaborated with 2 others. And so they're in visible, X-ray, gamma ray, infrared, X-ray and optical, X-ray, galaxy map, I'll come back to that for a second, exoplanet search, and a couple of them looking at the sun. So pay attention to the Gaia, the ESA telescope. Pay attention to that. they are making a map of our galaxies, 2 billion stars, and are going to have very accurate measurements of their distance and their true motion through the galaxy. And so they're redrawing the map of our galaxy in great detail. The 2 billion is a small sample, but it's still a pretty significant step forward in mapping, because our mapping has been imprecise. And they put out a new map every 6 or 8 or 10 months, whenever they. So, and it's very easy to get on and wander around this thing and see what their discoveries are. So it's ESA all the way. It's fabulous. Here's what's been retired. So how many was this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This many retired. 12, 14, 15, 16, 17, 18. About 20. Either working now or retired. And the first one went up in, what, 91? So that's not many years. We started this place, we built it in 2000. So most of these things have happened since we launched the McCarthy Observatory. So not counted here are telescopes on the ISS, telescopes on solar system probes, of which there are a lot. So what's coming next? The James Webb, we talked about that. Targeted first quarter 2021. It's had a lot of problems. If it works, it'll be by far the most powerful space telescope ever launched, with the most powerful instruments ever invented. So, and it's all in infrared, so you won't see the pretty pictures the Hubble does. But the Hubble's still going to be around there. There's nothing wrong with the Hubble. So we will peer back in time over 13.5 billion years, I left out the billion, to see the first galaxies born after the Big Bang. So we're going to be looking at the origins of the universe. But more is coming than telescopes. More sophisticated networking and alerts amongst all of these telescopes worldwide and in space. We're getting better and better at networking and relaying and sharing information. Scientists don't share well all the time, but they have to. So, and then there's this giganto integrated searchable databases for scientists, students, and the public. And so just announced a couple weeks ago was a big new release of what's called the MAST archive for space telescopes. This is something that is worth spending time at. Much enhanced so the general population can use it. I can use it. That's all you need to know. An enormous publicly available archive of space imagery, more from many space telescopes and some earthbound partners. It's amazing, easy to access. Just Google MAST archive, and you'll be right at the portal, and you can get your own little ID and just wander around. I spent hours wandering around M101 in different wavelengths and the spectra of things in M101. It's cool. It's cool. Okay, well, thank you.